Well, thank you for that introduction, and thank you to Rado and the organising committee for giving me the chance to be here talking today. It's been a really great couple of days. So in this afternoon session, we've been hearing about different modelling options we have. We started with Andreas Fell and the Quokka product, which is a really great way to optimise your cells. We just heard from the very impressive PV case, where we can optimise on the very large system scale. So it's probably fitting that we finish with SunSolve because we kind of fill the gap between Quokka and PV case. So today I'm going to be talking about SunSolve, how it works, and then I'm going to dive into a couple of ways that it can be used. And in particular, having a look at how we can take that digital twin, like Andreas was talking about, and actually project that into real-world conditions and how it's going to perform in the field. PV Lighthouse have been making specialised software for the solar industry for over 10 years now. We have a team of PhD researchers who are working on developing the models, and they also provide the support to our customers. This sort of modelling sometimes, it can be quite difficult to interpret, it can be difficult to set up the inputs, and so part of the value that we offer is that high level of support with our software subscriptions. SunSolve has been used in hundreds of scientific papers, so this is where it's validated, and it's also where you can see different use cases for it. You can see a little history of the development of the software. We started in solar cells and modules, and we've actually moved downstream into systems. And so that's a little bit different to everyone else who does yield modelling, because we actually started as cell and module engineers, and we've come at it from a little bit of a different angle. So we kind of describe it as being vertically integrated software. You can simulate something in SunSolve as simple as the optical response of a silicon wafer, which you might be using to check how your spectrophotometer is working. But then you could also start texturing that, you could add thin films to it, you could take the output of that and put it into Quokka, or you could start building actually a solar cell in SunSolve and then putting that into a module. So optics is really the strength of SunSolve. If you wanted to build a digital twin of your module, this is a great option. If you were looking at changing the types of EVA, the glasses and that sort of thing. But we can also continue that chain all the way down to the system space. And so we can actually make changes on the cell level. We might change the thickness of a single film, and we can have a look at how that's going to change the actual energy yield that comes out. I'm going to dive into this a little bit more later on, but as an example, you could sweep the perovskite thickness, solve the STC module power, but also get that energy yield out of that. So let's just take a little bit of a look at this kind of difference between the STC lab type conditions and the real world conditions. When we're in the lab, we tend to have standards, and the testing that we do, it's somewhat confined. We have a single incident angle, it's spatially uniform light, spectrum's controlled, the intensity, the temperature. We might vary those slightly, but for the most part, this is what we have. Once we go out into the real world, of course, there's quite a difference in the irradiance angle hitting the panels. It's coming from the front from different angles, it's hitting the back, it's spatially varied, there's variable spectrum, there's variable intensity, there's variable temperatures. And so modelling can really help us go from that first column into that second column. And if you're doing experiments outdoors, it's really hard to capture lots of different variations of that. And so we can use SunSolve to simulate the one you're doing and then project that into lots of different locations. So what does that require? We need advanced optics, and we use forward ray tracing. We need thermal models, and we need spectral models. And Andreas kind of mentioned this as well, is we're also looking for rapid solving. We don't want something that takes too long to get the answer. And so some of the decisions we make are around making these things quick. The yield solving in SunSolve takes minutes. Part of how we've sped that up is massive online parallel processing of the ray tracing itself. So we provide that for our customers. These are some screenshots from SunSolve, and you can see that it's capable of solving quite complex and detailed systems. It can do fixed systems, tracking systems, vertical PV, agri-PV. You can define modules with gaps and spacing between the cells for the agri-PV. And then you can even upload stuff from CAD files. So tracker companies are using this to understand how changes in their design might then flow through to changes in what happens in the module. So we ray trace that into every single part of each of the cells. So we ray trace into the cell level, We then apply an equivalent circuit model to get the electrical output of those cells. We can then join them together and get the output of the module. And so that gives us the ability to calculate the cell-to-cell mismatch losses that you would experience in any of these different situations. We use a detailed unit system approach. So if you look at that first picture, you can see the panels that are in blue. We're going to solve that in a very high level of detail. And this is very similar to what Andreas was saying with the IBC cell, where we just pick a repeating part of it to solve accurately like this. Now, in the system case, we might have 100 modules in that space. You could have gaps and different pieces of structure. To get that all the way through to some AC output, what we do is we take those module IV curves that we solved. The user can put those into strings. We solve that with SPICE. And so now we have string IV curves, and then we scale that result out to get finally an array IV curve, which will go into the inverter to get the operating point and the AC output. Just because you're a unit cell doesn't mean you can't get end-of-row effects. If you make the spacing on the end of your unit system large enough, then the repeating nature of that system no longer impacts the result. And so we can actually quantify the gains that we get at the end of row. Or if you're looking at a testbed system where it's a discrete size and you want to understand how this sort of effect would be impacting you, you can do that. You can see in the results here, the yellow dots are if we didn't add the spacing, and then the sort of the pinky purpley dots are the output of the modules once we have the edge effect in there. Now we can string those together, and we can limit that output because of the modules earlier in the string, and that's the dashed line. And so you can also quantify exactly what this will look like when you put those modules together. You can simulate the output of POA sensors in SunSolve. This is a comparison between a SunSolve output and a measured POA. That was on a system in Denver being run by NREL and FTC Solar. And you can see the very good agreement between the two, particularly in terms of catching all the little lumps, humps and bumps that go on in that. So if you are looking at outdoor measurements and you're trying to understand all the different effects that can go on, a simulation tool like this can be really useful because you can be varying things and having a look at, is that affecting my POA sensor or isn't it? And then you can understand, how does the POA sensor relate to what I'm measuring on the module itself, which also has applications in things like capacity testing. We have an extended temperature model, and most importantly, what we've extended there is we've added in the loss to the sky. We've also added in the loss to the ground and transient solving. You must use transient solving, particularly if you're doing short time steps. This particular model works very well. We've validated it at a number of different test sites for a number of different technologies, trackers, fixed systems. Once you apply this, it always improves your ability to predict the temperature of the module in the field. And you don't really need to add any extra variables because the sky loss is based on what fraction of the sky you can see, which we can solve, and what the temperature of the sky is. And finally, spectral effects. SunSolve calculates the direct and diffuse spectrum of light at every moment that it solves. And this changes because depending on the position of the sun in the sky and what atmospheric conditions we have. The ray tracing then continues to solve the wavelength dependence of the scene. So we have wavelength dependent albedo and the system structure. So all of that then interacts with the actual panel technology. So here's an example. We presented this earlier this year at the IEEE conference, where we looked at what is the spectral correction that goes on in yield forecasts for different types of technology. So looking at crystalline silicon, it's still significant. And then, of course, getting into things like the two-terminal tandems. So at different sites, you get quite different seasonal variations, and it just depends on how the atmosphere works at those different sites. Now, I'm aware it's the back contact workshop, so I thought we better put at least one back contact sweep in there. So in this case, what we're doing is we're varying the number of fingers per contact on the rear side there. Now, this is a bit of a simple example. Really, if we were doing this, we would work probably with Quokka to help calibrate the electrical model of that better. But at least what we're capturing here is the optical effect both from the front and the rear. So the bifaciality is changing, and also the series resistance effects. And we can find differences in where the STC power should be optimized versus in terms of two different locations. So somewhere in England where the weather is not very good, or somewhere in Australia where we have great weather. We can do the same sort of thing with tandems and bifaciality. So SunSolve is right now able to simulate the yield of tandems. We can have the AC output of any sort of tandem technology. Here we're looking at, first of all, 2 different thicknesses of perovskite layer and showing how the bifaciality of these modules is much more complicated than a crystalline silicon panel. It actually depends on how much light is hitting the front and the rear of those devices, and then again how thick you've got that perovskite layer. So should we be optimizing that for STC power, or should we be looking at it in the field? Again, we can sweep that in SunSolve. We can have a look at how that plays out in terms of STC power, as well as the yield benefits, whether that's bifacial or monofacial, and we can measure that bifacial gain on that system. So just to finish up, the last thing to talk about is something that's been quite popular as a way to use SunSolve, and that's in tandem with PV-Syst. So there are many times when a PV-Syst yield report is required, and that's just almost like the de facto standard, I would say, for the industry at the moment. But as an engineer, when you look at PV-Syst, you see a lot of inputs that are wide open, and you're not always sure how to set those, particularly if you're changing between different systems. So SunSolve has algorithms in it that allow you to calculate the inputs for PV-Syst. So we're talking about the bifacial factors, the rear irradiance, the front and rear mismatch loss, the shading factor, the transmission factor, and also the spectral correction. So you can take our spectral correction and put that into PV-Syst because it implements the first solar model, and the first solar model has coefficients. So we automatically fit those for you and give you those to use in PV-Syst. So this has been so popular that we've automated it, and now we're actually creating a report. So you'll have a report to use to justify your PV-Syst inputs, and that adds weight to your PV-Syst report versus other PV-Syst reports that don't have that, particularly where bifacial is involved. So with that, I'd just like to summarise that we've talked a little bit about creating a digital twin in the lab within your simulation tools. You can do that in SunSolve all the way up to the module level. You can do it on a cell level with Quokka as well. And so we calibrate that with these lab measurements, and we can do a range of things with that digital twin. We can do loss analysis, we can look at CTM, we can optimise design, but we can also then extend those lab results into the field. And that can help us simulate our outdoor module measurements if we're trying to understand what we're measuring on our test bed, or we can also assess performance as it's going to play out in the real world. Finally, we talked about enhanced bankability for PV-Syst, and that's one of the ways that you can also use this type of simulation. So I'd just like to thank ARENA, who have been providing us with some funding to help continue the growth of SunSolve. We have created this WeChat channel where we post when we have new features coming out. So if anyone's interested to follow that, please just scan that QR code. Otherwise, thank you very much for your attention.